Welcome to a brand new webinar from SIGGRAPH University about machine learning and neural networks. So we'll wait for some time to start while people roll in. Well, in the meantime, go ahead and post about yourself, where you're signing in from, what you hope to learn in this class. We'll give some more time. We'll start in 2 minutes. So there's a link in the chat that is a link to the drive. So I suggest you make a shortcut to this drive, and all the material that I post there should be accessible to you. The files should be read-only, but you can make copies of those and then edit them. Wow, somebody signed in from Perth. Awesome. It's noon here. I'm joining from Los Angeles, California. So again, welcome to this SIGGRAPH Now presentation of machine learning and neural networks. We'll have 3 webinars in this series, and they will be today, Friday, and the Monday after, the July 11th, 15th, and 18th. And so a little bit about myself. This is me. This is what I looked like before I had a beard. And I work at Spire Animation Studios as the VP of Engineering, creating a new pipeline in Unreal Engine to make a feature animated film. And before Spire, I spent many years at Disney Animation doing all kinds of things. So before we begin, I just want to read through this SIGGRAPH ACM anti-harassment policy. So again, please exercise consideration and respect in your speech and actions, refrain from demeaning, discriminatory, or harassing behavior, and be mindful of your surroundings and your fellow participants. So if you see any dangerous situation, please alert the moderators. And then in general, just be kind and nice to each other. So this course is coming to you from SIGGRAPH University. So SIGGRAPH University is a new charter with a lifelong committee from ACM SIGGRAPH. And our goal is to provide professional level, globally accessible learning resources to everyone. And through that, we will develop more courses like this and build professional development programs for computer graphics, gaming, and lots of different areas related to this. Also, we want to enable people to be mentored if you are looking for change in careers or different line of work, or you want to learn more about computer graphics and how it applies to different fields. This is something that we want to develop further. So you'll hear more about SIGGRAPH University as we go along. But that's who I am representing today and bringing this course through them. So again, before we begin, I want to thank everybody who made this course possible. First of all, the SIGGRAPH Lifelong Learning Committee itself, Jonali, Marianne, Mega, Aini, Janelle, Camila, and Cliff, ACM SIGGRAPH, the chair, Mumu, Alexandra from Smith Buckland, and Thomas, who I worked with to present this course last time. We're also featuring comics by a very talented artist, Mia Tang, And then again, a big thank you to you, because without you, there is no course. So let's begin. So we're going to be covering a lot of this course is going to be about neural networks, but I'll give you a general overview of machine learning. And then anytime you have questions, please stop and post it in the session. And if I am mindful enough to pay attention, I'll answer them here. If not, I will answer them in the beginning of the next class. So this is a general overview of like what all areas we will cover on different days. We'll go through them one by one. This is just for some housekeeping. Find this folder. And there are Colab notebooks there that I shared that you will use for today's sessions for some hands-on programming, and use the Ask a Question feature. And after the lecture, you can connect with me on Twitter with my handle here, or use the SIGGRAPH Now hashtag. We'll also record this course and make it available on YouTube if you want to watch it later. So general course overview. Today, we're going to cover some introductory material, Colab, data preparation, some frameworks, and then we'll do our first neural network for regression and classification. Friday 15th, we'll go into more details of some of the advanced neural networks. And then we'll wrap it up on Monday, July 18th, with some generative models and some more of the advanced neural networks that have become more popular these days. So today, we have a bunch of stuff to cover. It looks like a lot of material. So in this 3 days, we'll cover a semester worth of undergrad, grad level coursework. We won't get into deep mathematics of neural networks and machine learning. We'll cover enough to give you a general intuition and idea about how these things work. I'm not going to go through the entire list, but we will, as we cover it over time, you'll realize that by the end of the day today, you should have a very good understanding of what neural networks are, how to train simple neural networks, and how to program them for regression and classification. All right, so what is machine learning? So this is the first thing you want to ask, like, how do I use it? What do I use it for? In general, this is a longer sentence that I broke it up into different points. So each of those have meaning, and you want to make sure that you are solving the right kind of problem that we are able to solve with machine learning. So computer systems that are able to learn and adapt. So that's like one thing that you want to make sure that you are not just programming for one solution, that these systems are able to adapt to newer situations. So that's the main thrust of like why we want to use these. And these don't follow explicit instructions. So that you're not solving for a particular problem. You don't have a formula, but you are using algorithms and statistical models to take in a lot of data and analyze them and draw inferences from those patterns in the data. So it's just a longer sentence, but all of these things are important in terms of solving machine learning problems. So if you had a formula, you wouldn't just use machine learning because it would be meaningless. You have one solution and one formula that is accurate, and you would just use that. So in case you have a lot of data and then you want to understand it better and then want to see what patterns are there, so you can predict for the future or predict for unknown things that are not in the data. So that's when you would use machine learning. So machine learning is a subset of AI. So if you look at this big picture diagram, so there's a lot of things happening here. So AI is a field, and then machine learning is, you can think of it as a subset of it, where you use these algorithms that we will cover in the class to learn from data. Outside of that, there's a lot of things happen where you want to be able to collect data, you want to analyze data in different ways before you actually apply machine learning to that. So all of these things go together in a way which will become clearer as we go along. Any questions so far? So again, please stop me anytime if you have questions, if anything is not clear, or if I'm going too fast or too slow. All right, no questions so far. Everything is clear. So as you learn more, so there'll be like a lot of people want to know, like, what can I do? Like, what kind of job can I get if I become a machine learning expert? There are a number of jobs, so they all kind of work hand in hand, ranging from a pure software engineer to a machine learning engineer to a data scientist, sometimes also known as machine learning scientist or machine learning researcher. Um, so there's based on the function that you're performing in an organization, you may have a different role, and all these ideas that we present today, they're going to be applicable there. Based on your focus and desire, you can like lean towards one of these areas where you can become an expert. But there are plenty of jobs. There's a lot of demand for all these roles. So if you look at what happens in a very large organization that is deploying machine learning models and using them, there is even a bigger infrastructure setup side of things. So again, I'm not going to go through each of these boxes, but I'll make these slides available after the class so you can go into detail, or you can read the paper that this slide is based on. You can search for the name and the name of the paper. I have it here in the small type on the right side. So as you can see, it's not just simple machine learning. There's a lot of data prep. There's a lot of operations, what they call machine learning ops or ML ops, that need to happen in a large organization to make all this happen. Collection of data, cleaning up of data, coming up with features. And so the model analysis and data analysis, they are a smaller part of the whole. So the part that I've highlighted in orange, that is would be the focus of this course for the next 3 days. So there are other areas to be mindful of also that you can become an expert in and then get jobs. So this particular highlighted area covers simpler data analysis, data preparation and validation, training of the models, and model validation, and then as we go along, so we're not dealing with deployment of the model for production. We're not dealing with the initial data collection. We'll assume for our class that this data is given to us. So we'll cover all of these phases. So let's begin. Any other questions so far? So as I said earlier, we want to use machine learning for things that for which we have lots of data, and we want to make inferences from that data, understand the patterns and underlying structure. So this is an example data set which has a number of bedrooms. There's only one input, number of bedrooms, and then we are trying to predict home prices from that feature, number of bedrooms. So as a plot of this data, you can see that different bedroom sizes command different home prices, and you can already see there is some relationship between them. As we increase the number of bedrooms, the home prices do go up. There are some anomalies here and there, but in general, there seems to be some linear relationship. Traditionally, how we would solve this is we would try to fit a line. So again, this is a fabulous cartoon by Mia. It kind of gives you an overview of like what linear regression does. So you have all these points that are scattered around, and you are trying to find a line that best fits your data. So all you have is ability to change the angle or change where the line is. So it's going to be a straight line. So all the data are not going to fit on it, obviously. There's going to be some differences from where the line is and from where the actual data is. So this is one example of how we could draw a line that passes through most of the data, and the rest of the data is kind of scattered around it. And all these points that are not on the line and we're not going to be able to predict them. So essentially what we will use is, we'll use this line now to predict home prices. So somebody has, say, for example, ask for the home price of a 2-bedroom house. We would go vertically along this 2 on the x-axis, and then try to map it here to the left. So it's around 230. But actual home prices may vary. So, but this is how you would predict. So ultimately what you would have as your model is this equation of this straight line that you would use to predict. So again, this is another view of that. What we are doing here is trying to fit a straight line through the data points as close as possible, which would mean that sometimes the data doesn't really pass through the line, but it is close enough to each of those data points. So how we do that is you want to minimize this green line. So that is the error in your prediction or deviation from the straight line for the actual points. So your goal would be, how do we minimize these distances for all the points at the same time? So one way to do that is to use something called sum of least squares. And that's precisely what we do in regression. Assuming it's a straight line, because it's a linear regression, we say that the equation of the straight line is ax plus b, when then the actual data points are all the yi's, and you can find that error by taking the difference between the two. And what you normally do in sum of least squares is you take the square of that differences and sum it over all the data points. And then you try to minimize that squared error. So minimizing in mathematics, you do it by basically differentiating and setting that value to 0. And again, as you add in more data points, this equation would become a large summation of a square, and you would differentiate that and then solve for those a and b parameters. So a would be the slope and b would be the intercept. And that's basically how you solve for linear regression. And one way to do that, so the minimizing of this squared sum. So if you look at this, the squared sum is a square. It's a polynomial of degree 2, and it becomes a surface essentially. So if you look at that, it may be a surface that looks something like this, and essentially you're trying to minimize that. So as you minimize it, you set it to 0. So essentially you want to get to the lowest point on that surface. You do that by taking small steps, and each step you take essentially tells you whether you're still on the right path, because you can find out the slope. And as you take smaller steps, and ultimately you find a minima, which is essentially as close as possible to 0. The way to do that is to take small enough steps so that you're not jumping around. If you take very large steps, you may end up on these local hilly areas. You don't want to get stuck in a local minima. So you want to find the global minima, which is the lowest point on this surface. Another way to look at this is this would be a surface where you would basically walk along, and at each step you would see if you are going in the right direction or not, based on the sign of the differentiation that you did, and then at each step you keep walking down a little bit more. If you are going in the wrong direction, you adjust the parameters a little bit, and then ultimately you will reach your global minima. That's when you think that you have found the minima of all the sum of squares. So that's how you do gradient descent. So this particular way of finding the minima is known as gradient descent. If the equations were easily differentiable, and then you could just do the differentiation normally, but because we are dealing with numerical numbers of large numbers, we usually use gradient descent in machine learning to kind of find essentially you're differentiating. Any questions on this? All right. So another way to look at finding the slope, let me minimize some of these windows that I'm popping up. So another way to look at the slope of the line is essentially it's a linear function. So you can have two inputs, and then you basically do a weighted sum of those to give you the same equation of line. So it's just a different way of visualizing this equation of a line. And I'm just pointing this out because this would be useful when we get to the neural networks. And a second way to visualize this is using a matrix multiplication operation. Same things where you have these indices multiplied by the weights. So if you do the matrix multiplication, you do the column versus the row and multiply that and then add the sum. So all these are essentially the same equation, just represented differently. So that gives rise to our examples. So we had a straight line approximate our data points. So there are cases where the data does not conform well to straight lines. So in this example, this particular data, as you can see, there is no good straight line fit for this data. If we use a degree 2 polynomial, we can get a better approximation of the data set. If we use even higher degree of polynomial, you can do an even better fit. But in machine learning, we don't want an exact fit. So we want a general enough fit that is good, but not too exact, because otherwise you would have memorized all the data in your input and it doesn't generalize well. So there's always going to be a contention between how good your fit is. So this one on the left is called underfitting, where you don't represent your data with the model that you have. One on the right is called overfitting, when you have essentially memorized the data and then it doesn't generalize well. So the one in the middle is the sweet spot. So again, the way to find this is almost like an art form. So you adjust different parameters in your network and your training to arrive at that sweet spot so that your model, it fits generally well, and then it also generalizes pretty well. All right, let's see if any other questions. Awesome. So no questions so far on the content. So if you still have trouble accessing the files, just post it there on the channel and somebody will post a link again to you. So we looked at the linear regression where we were approximating things by a straight line. So we want to introduce non-linearity so that we can approximate different shapes of those curves, not just a straight line. And one way to do that is to just introduce another function called an activation function A here, which essentially is a function that looks something like the sigmoid on the left or the or the linear unit that you have on the right. So these essentially introduce a non-linearity into your calculations. And as you stack many of them, you should be able to approximate pretty much any function. And how that happens, so we'll get into that, like how a linear function can approximate anything, any kind of curve. I'll show you how. So in general, like a network node tries to stimulate an artificial neuron. So there is, it's a crude model of a neuron that you find in the body. Again, you have inputs, you have some kind of a summation operation, and you have an activation function, and then you have some outputs. It's not exactly like a biological neuron, but it's it derives some of its ideas and thoughts from it. So let's take a look at what a neural network looks like. So you have some inputs and you can add some more nodes. So again, looking back at how we formulated the linear equation of a line with a simple 2-node network, you can add more nodes here. So this is essentially adding complexity to your layer. So that complexity and the nonlinearity essentially allows you to represent and solve any function at all. So this comes from this universal approximation theorem. I'll not go into the mathematics of it. It's fairly complicated, but it essentially says that any network with a single hidden layer can approximate arbitrary, well-behaved continuous functions. So which means basically any function really, which is really cool because now you can have a complex network, which if you look under the hood, all it does is linear math, but it's able to represent data that may have a continuous functional distribution. Parallel to that, because now you can represent any function, but you think that we can solve general intelligence. But along with that comes a no free lunch theorem, which says that any algorithm that performs extremely well on a certain class of problems will then not do well for other classes of problems, which means we can have a specialized solution using machine learning for one class of problems, but it won't generalize to other things. So all the neural networks are great for solving specific problems. We can generalize them a little bit to solve a class of problems, like vision-based problems, but in general, it wouldn't be able to represent all intelligence. All right, so let's answer some questions. So first question from Aiden about demand for ML engineers, about demand for applications of ML at the place I work at or other studios. So this is perfect timing for reading this question because my next slide kind of tells you like where in computer graphics. So I work in the computer graphics industry, in animation particularly. And these are some of the areas, the slide that I'm showing, where we can apply machine learning, and we do for many of these things, especially for denoising and upraising. Naren asks, is there a methodical way to get the sweet spot between underfitting and overfitting? So there is not really. So I think it's all a matter of trial and error. And you'll see, like as you do more of these experiments, you will realize that how to do that. Subhash has a question about outliers. The best way to deal with outliers. So outliers are data points that were either erroneously collected or they represent something weird about the data. So the easy thing to do is to just drop them. Because they kind of show up and then they can mess up with your training. So this is where the earlier part of data analysis comes into play. Like you want to keep your data clean, although you do want to ask like, why did this data come in as an outlier? Like, is there something special about it? Like, for example, the home prices, you may see an outlier for a 3-bedroom house that is $3 million. Like, why is that? So you want to ask that question. Maybe it is closer to the beach, and maybe that's why the location is important as well. So that may give you more ideas. So maybe number of bedrooms alone is not enough. Maybe we need some other parameters like location. So then you can add more parameters for your training. So that will give you an idea. So don't just ignore the bad data. Just think of it as like, why is it there, and why it would have come. Maybe there is something that you're missing about your distribution. So, okay, so there's some people getting ahead of the lecture, and we'll come to these questions as we get to these parts in more detail. So for some of the applications in computer graphics, again, as I said, like we can do denoising. So when you do rendering in computer graphics, the Monte Carlo method for path tracing or ray tracing that is used normally, that has some inherent noise because it doesn't converge fully in the time that you have for rendering. So that noise can be fixed by using machine learning based denoising. There is also upres, because you can do very good upresing with machine learning these days. You can do style transfer from one content style to another. You can track your body and rigs to do some rough animation. You can generate brand new images for ideas, for stories and characters. You can do some character AI for games or for crowd solutions, where you can have some characters be automated and they're moving on their own based on some training that you do with machine learning. The other aspect is like, so a lot of these are image-based, some of them are non-image-based, like scheduling optimization. If you have a lot of things to render, what is the best way to render them, how many to render at what time. In large studios, you would often have hundreds of thousands of renderings that are happening as part of making the film. They usually have either in the cloud or on-prem, they'll have 30, 40,000 nodes basically just doing rendering. So scheduling for rendering, optimizing that, like how much memory to use, where to send the rendering to, all that becomes important. And you can learn that from the past behavior. And again, this would be specific to a studio where you like what the habits are, how people submit their jobs, when they expect them to get them back. You can train all those from past data and learn to schedule optimally. All right, so let's get into the neural networks themselves. So, again, this is an amazing a comic by Mia again that shows you like what a neural network looks like and how to train it. So essentially, you pass data from one side, and you have these weights, and we'll cover that, what it means in detail. And as you compute in a forward pass, you try to see what the difference is between a ground truth and the output of the network. And if the difference is too big, you try to adjust the weights. And these weights are adjusted via gradient descent, as we covered. And you repeat the whole process again. And over time, the weight is minimized, the loss is minimized, or the error is minimized, and then you get a set of weights that you would then lock in, and you'd say, okay, this is it, my model is trained, and now I am going to put through here any unseen data and can predict the output fairly accurately. So the way, again, this is in words, what was in the comic, you set the initial weights of the network randomly, you make a forward pass and compute the output, compare the output with the expected result, and that is your loss, the difference, and change the weights by a small amount and push the changes back all the way to the front and repeat until the desired minimization is achieved. Any questions on this process? All right, so for this seminar, we will use a Colab environment, which is a Python virtual environment provided by Google. Essentially, it's a Jupyter-derived Python IDE with TensorFlow support. It gives you machines that you can train on. It's free. So we'll be using that. In terms of software and tools, using Python and TensorFlow and some associated libraries, NumPy especially, that makes the data reading and writing very easy. Pandas is something that's like a little bit higher level than NumPy. It also helps in data analysis, and Matplotlib for plotting, and then Seaborn for some really fancy plotting that we will try. So for now, I want you to open this file. So there are 3 files in there: housing regression, flower classification, and then also housing data. So I want you to open housing data.py. I'm going to go switch to that. And I will have to make my video smaller and switch to that. I have too many windows, sorry. So you should be looking at this file. Everybody able to look at it? I'm giving you 1 more minute to load up this file, or you can just look at what I'm looking at. So I'm sharing this. All right, so this is what Colab looks like. So there's a usual file edit view stuff at the top line. Name of the file is housing.ipynb. IPYNB is interactive Python notebook. And this essentially follows the same rules as Python, except you can execute one group of statements at a time. And it's really nice to be able to do that on the web, so I can share and do things at the same time. So this would be like any other Python program. There are some things that you can add to these notebooks to give directives. We're just saying that we want to use TensorFlow version 2x. Usually it's the default now, but it used to be, we would have to choose between 1 and 2. We're going to import some packages that we'll use, the NumPy and Pandas and Matplotlib and Seaborn. And we're going to read in some data. So Pandas is PD, and this is what we would use to read data that is already available here. We're going to download it and read it. It's a comma separated value. So again, if you can hover over any of these and then look at the API, what all options there are for these calls, we will use the minimal set of API. Again, this is not an exercise in programming. This is more illustrative. Many times I would not write code like this in production, but because I want to be as explicit as I want to be to make sure that you understand each of these steps, this code may not be optimal, but it is very illustrative. So you read the file, you say separator is a comma, and you read the CSV file. So I'm going to execute this set of statements by pressing this play button. I'm going to read the data. And this is just an exercise to kind of get you familiar with Pandas and Python and data analysis a little bit. So shape is what this matrix is. It reads as in as a matrix essentially in NumPy. And it says that there are 17,000 data points with 9 parameters. So it's a 17,000 by 9 matrix. So let's look at some of the data points. What are in there? So there are obviously labels, and there are these, the head statement here prints 5 of the data points. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9 parameters, as you can see, the longitude, latitude, median age, rooms, etc. And these are the numbers that you get out of that. So you want to make it a habit to kind of look at the data, make sure it makes sense or not. So this is one way of looking at, because it's all spread out. We're going to transpose this so it's a little bit easier to read. So this way, the parameters now on the left side in a column instead of in the row, and then the data goes from left to right. So in just a transpose of the earlier matrix. So let's look at the data and see what it says. So there is obviously the location, latitude and longitude, the median age, total rooms, total bedrooms, population, household. So right away, you can see that total rooms is like such a large number. What does that even mean? And total bedrooms is such a large number also. So this data is about a block at a time. So it's not per house. It's data about one block of housing. And that's why you have this total rooms as a largest number. So now it makes a little bit more sense. Median income in that block, and then median home value in that block. So that's good. So data looks good and clean. We can also ask it to describe some of the statistics of the data, where it says what the mean is, what the median is, and what different percentiles of the data are. Because we have too many parameters here almost to look at, let's dissect into two of the parameters, latitude and longitude. And you can do that by just indexing them in the data. So now we can do is do a plot of this data. So there you go. So this particular plot, we're using a Seaborn to do this plot. And we're saying x-axis is longitude, y is latitude, and size is the home value of each of these dots. And then the color is also the mean value. So the darker the region, the higher the home price. And you're just going to draw this. Height is equal to 8 inches. So this is the data. So as part of data analysis, it's very useful to plot these things and look at it. So right away, you can see this is essentially data from California, because it represents a map of California. Now the data is laid out in the longitude and latitude. So you can even identify some of these regions where things are densely populated. So this is most likely Los Angeles. Los Angeles is probably around 118 west and 34 latitude. So this is Los Angeles and related areas. And then you have San Bernardino here, this pretty sparse area here. As you go into the Bay Area in California, you see another dense population. And then this line, straight line right here is pretty San Diego at the bottom here. And then Mexico down here, and then same thing with the top side of the data. You can also see that the median home value is larger along the coast. As we say, location is really important for home prices. So you can get a lot of information just by plotting data in different ways. So that's another good habit to have, is to just understand your data before diving into models, because sometimes people have this urge to kind of just dive into machine learning without looking at the data, without understanding that data. So another type of plot that is useful is to just plot every attribute against itself and against other attributes. So we can take 6 of these or 5 of these and do a cross plot of everything. So this thing is called pair plot. And you would also essentially, you'll get a grid of different things versus different things, except in the diagonals. The diagonal, what Seaborn does is it gives you the distribution of the data as a histogram. And rest of them, this because it's plotting every attribute against every other attribute, it should be symmetrical along the diagonal. So if you flip it, they should be essentially the same graphs. So we only have to look at essentially the top diagonal side or the bottom diagonal side to get an understanding of the data. So one thing you'll notice is that we took only 1,000 data points, because there are too many data points. This plot becomes takes too long to plot, and so we took only 1,000 data points. If you look at now the latitude versus longitude, let's see, this is latitude versus longitude, either this or that, we don't see the map of California anymore. Why do you think that is? You can answer in the chat. Anybody? All right. So yeah, so somebody said sample size, and somebody said vomited, and I think they meant omitted. Right. So when we get the first 1,000 data points, they are not random enough. So they're picked from the top 1,000, and they are not representative of the entire data set. So we may have picked it from one local region. So that's why they don't make sense as a whole, because now they are not representative of the entire data set. So what you would want to do is get random 1,000 points instead of the first 1,000 points. So this is again going to be a common theme where you always want to make sure that your data is representative of the rest of the data set, or your data set itself is representative of the entire distribution that is possible. So what we'll do is, to fix that, we will use a call called sample. So I'm just going to paste this. Bear with me, I have too many windows in here. So, sampler. So let's see if that fixes it. So this sample does random sampling from the data set of the given data set, and we're asking it to get the random 1,000 points. So now you can see it represents the map of California still, even though we have only 1,000 data points. So compare that to the rest of it, where we had plotted all the points. Okay, so that's how you do a little bit of the data. The field is pretty big. You can do all kinds of things, all kinds of plots. You can normalize data. You can figure out what's going on wrong. You can find out the outliers, something like this. You can also look at like what has an obvious relationship. So the population and the total bedrooms has an obvious linear relationship here. You can learn a lot from data without doing any machine learning at all, just by looking at it in different ways. All right, so let's come back to the presentation bit. So in general, like you would be given not some data initially. When you try to solve problems, you will have a problem to solve, and then the data is what you would collect to solve that problem, right? So once you have that, you want to see like, what are you trying to answer? What are you trying to predict? And then you go about collecting the data and clean it and prepare it and analyze it. And so we did the first 3 steps, like, okay, we're trying to predict home prices. We collected some data, we did some analysis, and then we are going to do some feature processing, which is transform the raw data. So because some of these things have different ranges, right? So if you were going by square footage, that would be meter squares or feet square. And the other data, like number of bedrooms, is 1, 2, and 3. And that's they're different units for different data. So sometimes it helps to transform them into a better unit, or to scale them proportionately so that they all in the same range. It makes it easier for the network to learn. So it doesn't change a whole lot. I mean, you can keep them, it should be fine, but it just takes sometimes longer to learn from the data that is not close together in terms of ranges. And then we build the model. So again, look at that, like model building comes so far down, and then you design and build the learning algorithms. So do we use a neural network? Which kind of neural network to use? How to set up all your parameters for the neural network? And then you train the network. So you feed the data, and the process that we looked at for a neural network, where it adjusts the weights and evaluate the quality of the model. And then finally, once your model is ready, you're happy with it, you take that model and deploy it, and you start predicting from that model. So this is the general solving process that I would like us to follow for any kind of problem you're trying to solve with machine learning. It's fairly general, but it kind of emphasizes that model building, which is what a lot of people want to focus on, is just one part of the entire process. So let's apply this process to a machine learning problem with all this new data that we have. So what are we observing is the parameters related to the homes for a census block. And then we want to predict median home prices for the block. So that's our framing of our problem. Let me make this full screen again so you can see better. So second part is data collection. We collected the data because it was just given to us. We didn't go about creating a census. So in practice, you would essentially look for data from home sales, Zillow, other places. You would do a survey, and that's how you would collect all this data. And then you would use some of these methods in NumPy or pandas to look at, like, some of the data might be empty, or some data may be outlier that you want to drop. So these three functions kind of would let you find where the data is empty. You want to drop some of the columns altogether, features altogether, and or if you want to clean up your data in any way. So this is the opportunity to do that. And then we do the analysis, which we did a little bit. We did the pair plot. We look at the statistics of the data using describe. And then the next step is feature processing. So this is important part where you would, as I said, like, you can sometimes normalize the data to where everything can be brought in between 0 and 1 by just applying this function, which just takes the difference of the max and the min and uses that for each input to kind of put it between 0 and 1. Another way to do that is standardize it. So not just like normalize it, but also make sure that it has a standard deviation of 1. Another thing we do in machine learning or neural network training in particular is that we want to keep aside some data for testing. So it's because if you train on the data and you test on the same data, you're essentially dipping into the data that's already been trained on. So it's not clean, right? So your testing is not considered clean because you've already used that data for training. So you want to be mindful of that. And then in the beginning itself, keep aside 20% or some percentage of data aside for testing. So, and then the third thing you want to do is you want to separate the features from the labels. So the label is essentially, in the case of regression, is the true value. True value is what you collected in the data. And the features are all the input properties, right? Like the number of bedrooms, latitude, longitude. So all these are features, and label in this case would be the median house value. So the way you separate it is we want to create two variables. The first thing we did was we separated testing from training, and then now we separate within training, you want to separate the X and the Y. So X we would call the features and the labels would be Y. So you would take everything, every feature column except the median house value, and would assign that to the training data of X, and then the ground truth or label in this case would be the median house value column. Everybody clear on this part of the processing? So Addison Grant has a question about a validation data set. So validation data set is something that some of the APIs that we have, they can do that automatically. And you want to, so the idea is for behind the test data set is that you test it when your network is ready. While you're training your network, you may want to make a number of adjustments. When you make those adjustments depends on you entirely. There is also a process you can follow where you adjust weights after doing some validation. But the validation can come from the training data itself. So think of the validation set as a subset of the training data that you can try it on temporarily, because you don't want to try it on the test data. You want to try the test data only towards the end once you're happy with your model. So while you're adjusting the model, you may want to use yet another testing set for that is called the validation set. So then you build the model. So you build the model by choosing a network. So this particular case, what I'm showing here is something called a fully connected model, and which is obviously Y because everything is connected to everything. So you have some input nodes, you have in between layers. So these are called the hidden layers, the yellow and the orange, and the green is the output. In this case, we have only one output, that is the median home price for the block, and our input layer would be 8. Because we took away the median home price from the 9 input features we had. We have 8 input, and then feeding into this network. And we can have as many hidden layers as we want. And the more you add, the more complex the network becomes, the slower it becomes, but also it may become more accurate. So the way to do this in TensorFlow, we are going to use something called Keras. And again, this is not going to be a class on Keras or TensorFlow. I'm using this Keras because it kind of aligns well with the way I'm teaching this course. So these networks and these layers, the Keras API provides a very nice mental mapping from the networks into code. And there are other APIs, other toolkits like Torch, which do similar things, and they do it very well as well. A lot of people use them. So again, it's up to you to choose whatever you want to use, but most of this course will be following TensorFlow and Keras. So essentially, we just line them up. You have some input, and then you have the different layers. So you have dense, meaning fully connected. And each of these nodes that you have in the dense layer, in case I'm specifying 32 nodes, and each of them will have an activation function. So activation function, remember, we had 2 examples of either using a sigmoid, which is an exponential function, or using this rectified linear unit, which serves the same purpose, but it is faster to calculate, and that's what most networks use. You can provide it a name, and then you have 2 parallel layers, essentially the same structure, and then your output layer is the same. So this all basically specifies the structure of your model. Again, it doesn't do anything yet, and it's only specifying the structure of the model. And next thing you want to do is compile this model. So when you compile the model at that time, you can specify what kind of loss you want to have or you want to optimize for. So most common loss in regression is mean square error, which is what we're specifying here as MSE. And the way the optimizer works, this is the back prop part of it. We specify that we're using this thing called RMS prop. And the number in here is something called a learning rate, which is how fast or how quickly the weight change can occur. Quickly meaning like how large or small. So remember, when we're doing gradient descent example, you want to take small steps. If you take too big a step, you may keep jumping around without kind of minimizing. So the learning rate essentially, which is this number 0.001, it tells the system like how quickly to go about adjusting the weights. And then you have some metrics you can measure. So your loss is already mean square error, but you can measure other metrics as well. So I'm also put in here mean average error, which is essentially mean square error without the squares. And then you can look at the summary. Again, all this is just setting up the model. Nothing is being run yet. And then next thing you do is you train the network. So it's always a good idea to kind of just take a sample and try to predict it. And obviously it won't do anything useful. It will print random results because we haven't trained the network yet. So in the next line, model.fit is how you train the network. So here you give it the training data, both the input parameters and then the ground truth. And then you specify some of these parameters. One is called the batch size. So what you can do is you have 17,000 data points in your data set. You divided them, like reserve 20% for testing. So you're left with 80% of that. And then you can take each row of that data, push it through the neural network, adjust the weights, and then keep repeating that, right? So you can treat one row at a time and feed it to the network. That becomes very slow. So you don't want to keep adjusting weights after every row. So batch size essentially says, how often do I adjust the weights? So here we're saying only adjust weights after 32 data points have gone through. And epochs is the number of times you run the entire data set through. So you want to be able to kind of repeatedly take the entire data set and run it through. So you can think of it as a loop that is running through all your data set 10 times and takes one data row at a time, feeds it into the network, and after 32 rows have gone through, it will adjust the weights and so on. And this is a validation split where we can use that for figuring out like if the network is converging or not. So again, instead of using the test data, which you want to reserve for until later, you normally use a validation data to test it. So after the training is done, we plot the loss and the validation loss. You want to make sure the loss is going down over time. And then you, if it is not going down, something has gone wrong with your model or your data, you want to revisit that and fix that. And then, so when you are training this, so you'll hear all these terms and they're all kind of synonymous of each other. Sometimes you will hear features or attributes or X, that is your data set, and output as Y or label or ground truth. And your network is also sometimes called a model. Your loss function may be called metric or cost. Activation function, we described it as nonlinearity, and sigmoid or rectified linear unit is two of them which are used pretty often. And training, which I've been calling training, is called fit in many packages. And this is the optimization process to minimize the loss function. And then prediction is also called inference, which you do on the test data. And then finally, when you deploy, you do it on the unknown data with unknown output. So everybody clear on this process? Right. So another question by Subhash is like, how can we get all the functions available? So you can go to the API. So there's TensorFlow API documentation. It's pretty comprehensive. It's very good. So it has a lot of examples. So you can get overwhelmed by the amount of API functions available to you. So for now, if you stick with what's in the course and then explore more later, I think that's what I would recommend. And the same thing because we've introduced a number of packages. We have introduced TensorFlow, Keras, Pandas, NumPy. They all have APIs. They all have hundreds of thousands of functions, and you can use any of them and mess up your data pretty badly. But you should feel free to experiment. And for now, I think instead of kind of making this a class about TensorFlow or Pandas or NumPy, I want to keep it on the process, and then I want to keep it on you so you can learn the terms that we are using here today and then how to do these. Another question by Ibrahim, why are there 32 neurons in the hidden layer? Great question. So again, there is no hard and fast rule. You start with whatever you want, and you can adjust it. You can make it more. In general, the more parameters you have, the more nodes you want. And so these are all perfectly fine to start with something small and then expand as you go along. There is a penalty for using more in terms of complexity and time. And you can not only just use more nodes per layer, but you can use many layers. So there's two ways you can increase the complexity, and each of those methods will add a significant amount of time in the computation. Because if you look at the connectivity, everything is connected to everything, which means a lot of communication, a lot of parameters, a lot of weights to compute. So you're depending upon how much memory you have, how much compute you have, you can experiment with different things. And then if you run out of those, you can always go to the cloud and use and pay real money to kind of get more powerful machines with a lot of memory, a lot of compute. All right, we'll come back to some more questions. Let's try to, so the last part of this would be like predictions. Once you're happy with your model, you want to start predicting. The predicting is just this call predict, and you give it the test data and it will print out the results, and then you will plot the results. So the thing is, at some point, your data will become so large that you can't really look at the actual values. You want your network to work in general. So you want to look at the statistical distribution of a prediction instead of actual results, because they may not mean anything if you look at only 5 or 6 data points. Remember, your network is once trained and well trained, it's supposed to predict for any kind of data that comes along that follows a similar distribution to the given data. So you don't want to focus on 1 or 2 results from the prediction, but you want to focus on overall statistical nature of your prediction. And we will get to that as well. So these are the 7 steps. Let's apply them to this data set that we looked at. And I am going to switch to this other notebook. It is called Housing Regression. And if you can see my screen, I'll make this a little bigger, so I feel like it's a little tiny. Much better, huh? So Same thing, we import all the packages that we need. We're reading the same data. So this is how you would drop the empty data. So you're saying here, anytime the data is missing, you just drop it. We normalize the data. Again, just using the max minus min difference and then divide everything by the. So let's look at this data. Make sure I press that. All right, so this data now, again, if you look at the min and the max, they should all be between 0 and 1. This is the min and this is the max. Let's look at the statistics of the data again. So again, we have 17,000 data points. So next we are going to do is, again, remember the sample that we used earlier. So we're going to use the same thing, but instead of number, we're going to, because we may not know beforehand how many data points are there. So instead of using manually taking 20% or 80% of 17,000, we are just going to say, just take the 80% of whatever the thing is. And then you want to take a random sample. You don't want to take the top 80% or the top 20%. So this would, again, remember the example that I showed you from the map of California. You always want to keep the data outside for testing, but it should be representative of the rest of the data set. So we're always going to sample instead of taking the top 20 or the top 80. So training data and test data. So we got the 80% here, 20% there. And then we are going to separate out the training and the ground truth for features, and then the same thing for the testing data. We also want to separate it out into X and Y. So let's see what that looks like. So now if you look at that, the training data has only this, that's the 80% of 17,000. And the test data has 3,400 elements. So now we should look at how many parameters we have. It's 8 parameters. All right, so we can count it like this: 1, 2, 3, 4, 5, 6, 7, 8. And the thing is, you want to do everything by computing it rather than putting in hard-coded numbers in here, because for some other data, they may change. So you want to keep that in mind, like where you get these. Again, these API things are, this is part of pandas. You can just use that. So this is where we are building the model. So we are making an input layer. Again, these API methods give you everything you want to be able to set up. Most likely the default should work pretty well. And you have 2 dense layers, 32 each, and you're using rectified linear unit. You have 1 node in the output for the median home price. And then we're setting the learning rate to be 0.01 and setting the loss to be mean square error and the metrics to be mean average error. We want them to print a summary of the model. So this is how you get to the summary of the model. So you look at the summary and you'll see that there's a number of parameters in the model. So just this simple network has a lot of parameters already. And how did they come about? What are these parameters? So you notice that we input 8 items from the left, which is the feature set. And we connect them to 32 nodes in the first layer. And this is how you get 8 times 32. And there are 32 extra nodes that TensorFlow will add for you automatically, which is 1 per node. These are called the bias nodes. And they serve the same purpose as the bias in the linear regression, where you had equation of line as y equals mx plus B, and B was the intercept. It serves as the bias in linear regression. Similarly, every node has a bias unit. So ultimately, you'll end up with 32 bias unit in the first layer. So this first layer itself will have 8 times 32 plus 32 parameters, and this is where the 288 comes from. The next layer grows pretty complex because now you're connecting 32 nodes in first hidden layer to the 32 nodes in the next hidden layer. Everything is connected to everything. That makes it 32 times 32 plus the 32 bias nodes, and that is where the 1056 comes from. And lastly, the final layer, you have one output node and 32 from the final layer is coming into this node. So there are 32 times 1 plus 1 bias node. So there's that 33 comes from the total. If you add these up, they add up to 1,377. That's the number of parameters. So a seemingly simple network already has a number of parameters to train for. So any questions so far? Let me look at. So Parisha has a question about choosing the parameters or the features, like more number of features, do they mean better results, especially when all of them are correlated with the results? So yes, in general, more features will give you better generalization. Like, for example, think of the home prices themselves, right? So if only given the number of bedrooms, we know that that is not enough to make predictions. We know that some small bedroom homes are expensive. We know that location is important to housing prices as well. In fact, it's probably the most important feature, and we should add that. So once you have these two, then you can think of other features like square footage of the home. Maybe that is important too. Maybe number of bedrooms. You can see that number of bedrooms is a proxy for square footage. So maybe you can get rid of number of bedrooms and use square footage as an actual feature. So you can eliminate features. You can see what features are causing kind of a duplication of information, but you add, sometimes there are features that are, you don't even know that are important. So the classic example of that is from Uber. So they had this machine learning trained model where it would predict when people are more likely to pay surge pricing. So surge pricing is when the traffic is too much and it takes longer. People would pay more. So they trained a model for that, and they added this one parameter, which didn't seem to, at first glance, make any difference. You would think, why? So they added the battery power remaining in your cell phone. So the battery power remaining in your cell phone was a very big predictor of how likely people are to pay for surge pricing. So you can understand now in retrospect, like, yeah, that makes sense because people are anxious and they want to get somewhere before the battery is dead, or use the Uber itself to charge. So that kind of makes sense, like seemingly unrelated feature that you add to your training set, and ultimately it kind of makes a difference in your answer. All right, so let's look at, so there's another way to, we set this essentially a diagram of this network, right? So there's a better way to plot a diagram in TensorFlow, which has this utility called plot model, which does it a little bit more graphically. It's essentially the same thing. And now we're going to train it. So we're going to do a batch size of 16. For 10 epochs, we have validation split, and we're going to make it verbose so you know what's going on in each step. So it's going to start training, and let's look at what happens. So this is pretty quick. Again, we have 17,000 data points, then split up between training and testing, and they are going through the entire network 10 times total. After every 16 data point, which is our batch size, we update the weights, And this is all this multiple for loops here in this method that kind of happen behind the scenes for you. And each step, it tells you what is happening and how the loss is progressing, both the actual loss and the validation loss. So at some point, it will stop after running through all the 10 epochs. And we look at this. In general, you want the loss to go down over time. And if you look at both the validation loss and the overall loss, it should be going down over time, which is it is. So it's a decent model. Things are going down. Both also look at the mean average error, it's going down as well. So decent model, but sometimes you'll have a lot of these things and you don't want to sit here looking at this and comparing numbers. Again, you want to graph this. So let's graph this. So the history part in this fit, once you call this fit method, it will go through the bunch of for loops, do the training, and it will put all this resulting data in this history structure. So we can tap into that and we can plot it. So it will have a few things called loss and validation loss, and we can do some nice plot and look at different things. And let's see what that looks like. So you can see we plotted two kinds of loss, the training loss and the validation loss. So again, remember, validation is like some of the data set aside to do testing. It's not our final testing data, but it's just validation. So you look at this, it's going down. This is jumping around a bit. Not bad. And you look at the overall losses. And the thing is, at this point, you don't want to go into prediction from the test data because you want to adjust this. You want to make it smoother and nicer and go down a little bit more. Can we make it happen so that the loss goes down further? There are a bunch of things we can adjust here. So let's do that. So there are many things we can adjust in a model. One is the model itself. We can, as I said earlier, we can make this denser. We can make this deeper. So let's make it deeper. So we'll add one more layer. Again, exact same thing. We just call it something different. We've added one more layer. So we'll create the model again. And now if you look at that, we've added more. So our number of parameters has kind of exploded. So this is called the curse of dimensionality. So anytime you make your network more complex, the number of things to compute increases exponentially. So you want to be mindful of that. Things will explode. After some certain point, you won't have enough memory or enough compute to solve your problems. So let's look at this model in a graphical way. So you have one extra layer now. And let's try to train this. So remember, the losses look like this, and the graph look like that. So let's see if we can do better by increasing the complexity of the network. So as you'll notice, it'll get a little bit slower now. And there's the graph of this. Loss is a little bit better. So another thing, so we adjusted two things. One more thing we can adjust is we can let it run for longer. 20 epochs now. And then we can also do is maybe go slower. So again, that didn't change the number of parameters. all it will do is go a little bit slower, train for a little bit longer. So 20 epochs this time instead of 10. Awesome. So let's plot this. So it's going down further, looking good, it's better. So this is the kind of general shape you want. Ultimately, it should approach, and these things should align in themselves well if you run it for longer. And let's evaluate our model, and then now predict from the test data. So all you need to do is call this predict method, give it the test data, and we'll give you the output. So as I said, we have a lot of test data here, like 20%. So we don't want to look at each value. You want to just plot them against true values. So we're going to plot true values against predictions. Anybody wants to guess what shape this should be, ideally? Yes, no? Okay, so this should be a straight line diagonally. So this is prediction versus true values. If the prediction matched the true values exactly, you would get a straight diagonal line, and all the points would be on that line. But because we're not going to be able to do precise prediction, that's the nature of machine learning algorithms in general. We are making a general enough prediction so that it matches. So you see that most of the predictions do lie around this diagonal. There's some outliers which we can look at data like why that is happening, but pretty much most of the errors are around the diagonal. So that's one way to look at it. Second way to look at it is that what is the nature of these errors? So that is, we'll plot a histogram. So in general, the errors should be normally distributed. And this comes from statistics where we are assuming that all these input data that we get, they are identically distributed, independent and identically distributed. And if you look at that, that has a mean of 0, which means all these data were exact matches from prediction. And the rest of them, they should trail off as you get away from the actual prediction. The few of them will be on the left side, few of them would be from the right side. So this should follow a normal distribution where the mean or the average is somewhere in the center, and then more unlikely events, as you call them, happen at very low frequencies on the left and the right side. So that's how you do. So this is when we went through the entire process of looking at the data, building the model, training it, evaluating the results for a regression. Any questions so far on this? So Oliver has a question about, like, if you use the same training data set and adjust your model after reviewing the results iteratively, wouldn't you introduce bias and start overfitting your data? So the answer is, like, you want to be able to tune your parameters. And the only opportunity you have is like right after the training, you see, okay, you're not getting the results you want. What should you adjust? And you're going to run it again. So you're going to build your network afresh. And so you'll avoid biasing your data. On the other hand, if you had used test data as well, you will introduce the bias in the testing data, because that would be used in the learning process. So as long as you keep the testing data separate and don't use it while adjusting those parameters, you should be good. Okay, so going back to the presentation. So the things that we adjusted while we were training, these things are called hyperparameters. So all these things, like increasing, decreasing the number of epochs and different batch sizes, different learning rates, different optimizers, different loss functions, make the network deeper or denser. All of these are called hyperparameters, and that is adjusting them is also almost like an art form. Sometimes people just run a matrix of these values, different values through the network, and then parameterize your model based on these different values. So you can imagine like having a large array of different values of batch sizes, different values of learning rates, different optimizers, different loss functions, and you basically have a combination of these that you run your experiment again and again, and then just pick the one that gives you the best results. So as an exercise for your homework, go ahead and like in the regression for home pricing, just try it out, different values, try different things and see what makes a big difference, what doesn't make a big difference. All right, let's see how we're doing on time. So we're almost out of time. So we didn't get to cover the rest of it, which we will cover next time. In the meantime, what I'll do is we'll capture all these questions that I didn't get to answer in the beginning of the next class. Recording will be available for this lecture, and I hope to see you all on Friday. So I'll also make the slides available next time. When you meet, you can kind of revise those a little bit and then make sure that you have read through the slides, and then any other questions you might have, you can answer that next time. So we'll pick up the pace next time, go through a lot of different things, some math, and see you all on Friday.